All right, let's talk about something huge. We're going to tackle one of the absolute biggest ideas in all of science, Einstein's theory of relativity. And we're going to see how it completely flipped our understanding of gravity on its head. So let's just dive right in. To get us started, I want to ask a question that might sound a little crazy. Is gravity actually a force? I mean, we feel it every single second of every day, right? But what if the answer isn't what you think it is? The answer might just blow your mind.
For hundreds of years, we were pretty confident we had gravity all figured out. But the truth is, that classic understanding was built on a model that had some really deep, really strange problems. Problems so weird that they even stumped the guy who came up with the theory in the first place. We all remember this from science class, right? Sir Isaac Newton, the apple falling from the tree. He gave us this idea of gravity as an invisible, universal pull, a force that every single object with mass exerts on everything else. And look, it's a fantastic theory. It explains why things fall down and why the moon orbits the Earth. It's simple, it's elegant, and for most things in our daily lives, it works perfectly. But it's not the full story, not even close.
And these weren't exactly secrets. Even Newton knew something was off. First off, get this. According to his theory, if the sun just poof, vanished, we'd feel the gravitational effect instantly. That would mean gravity travels faster than light, which basically breaks the #1 rule of the universe. Then there's the fact that it's just so incredibly weak. I mean, it holds entire galaxies together, but you can use a tiny fridge magnet to defy the pull of the entire planet Earth. And maybe the weirdest thing of all, how does gravity know how to pull on a bowling ball and a feather with just the right strength so that they fall at the same rate? All these little inconsistencies were pointing to a much deeper truth.
And this is Newton, in his own words, basically admitting he's stumped. He's saying, look, I know how it works. I have the math, but I have no idea why. He knew he was looking at a shadow on the wall, not the real thing.
So to solve Newton's puzzle, we have to do what Einstein did. We have to completely change the way we look at the very fabric of the universe. We need to follow the clues he found that allowed him to piece it all together.
Okay, here's clue number 1, and this is a total game changer. Einstein asked us to stop thinking about space as just an empty, boring backdrop. Instead, he wanted us to imagine it as a real, physical thing, a 4-dimensional fabric he called space-time. Think of it like a giant trampoline, or a huge sheet of jelly, maybe a big block of Hawa. It's not just nothingness, it has properties. It can be stretched, it can be compressed, and most importantly, it can be bent.
So what happens when you try to move in a straight line on this bendy fabric? Well, on a flat surface, a straight line is, well, it's a straight line. But if the surface itself is curved, the shortest path, the straightest possible line you can travel, is going to follow that curve. Now just remember that. An object just moving on its own will always take the straightest possible path it can through space-time.
Let's move on to our second huge clue. It turns out the universe has a speed limit, and it is absolute. And there it is, the speed of light in a vacuum. This is the ultimate speed limit in the cosmos. Nothing with mass can ever reach it, and absolutely nothing can go faster. It's a fundamental constant. And you can see how this was a massive, massive problem for Newton's idea of gravity acting instantly across the universe.
So we have our 2 clues. Space-time is a real physical fabric, and there's a cosmic speed limit that you can't break. Now, let's see how Einstein connected these with a brilliant thought experiment that would change physics forever. The story goes that Einstein was just looking out of his office window and saw a painter or worker fall off a nearby roof. Now, thankfully the man was okay, but watching this happen gave Einstein what he later called the happiest thought of his life. Okay, so let's really break down this thought. From our perspective on the ground, the worker is clearly accelerating because of gravity. But from the worker's perspective, for those few seconds, he feels completely weightless. If he dropped his hammer, it would just float right there next to him, just like an astronaut in orbit. He feels no force on him at all. Now in physics, a state where you feel no net force is called an inertial frame. So here's the paradox. How can you be accelerating and be in an inertial frame at the exact same time? It's a direct contradiction. And for Einstein, that meant one of our core assumptions just had to be wrong.
And that leads us to the critical question. If the person who is supposedly experiencing the force of gravity feels absolutely nothing, then where is this force? What if it was never there to begin with?
And this is where all the clues just snap together perfectly. The paradox of the falling worker leads us to this incredibly elegant and profound answer that just solves all the strange problems we started with.
So, here it is, the big reveal. Gravity is not a force. It's not some mysterious pull reaching out across the emptiness of space. The falling worker felt no force because there was no force there to feel. Instead, gravity is simply the shape of the universe. It is the effect that mass and energy have when they bend and warp the very fabric of space-time around them.
Let's go back to our sheet of halwa. You put a heavy bowling ball in the middle, and it creates a big dip. Now you roll a smaller marble nearby. It's not being pulled toward the bowling ball, it's just following the straightest path it can along the curved surface. Well, that's exactly what's happening with the Earth and the Sun. The Earth is just trying to move in a straight line, but it's moving through space-time that has been warped by the Sun's incredible mass. What we perceive as the force of gravity is just us moving along these curves.
And this new understanding just beautifully solves all of Newton's old problems. Does gravity act too fast? Nope. Ripples in space-time, what we call gravitational waves, travel at the speed of light. Does it need to adjust for mass? Nope. All objects, big or small, follow the exact same curves in space-time. And is it a weirdly weak force? Well, that one's easy, because it's not a force at all. It's just the geometry of the universe itself. So think about that. Gravity isn't a force pulling you down into your chair. It's the universe itself, the fabric of space-time, curved up and around you, pushing you along your path. It's a complete shift in perspective that reveals a universe that is so much stranger and more beautiful than we ever imagined. And it really makes you wonder, doesn't it? If we could be that wrong about something so basic, what else are we completely wrong about?